All right, now the stability of benzene. So the stability aspects of benzene is remarkable, and we need to spend some time on it. It's gonna help you understand some other things later on. So recall that in general, alkenes from chapter 7 or 8 maybe, alkenes readily undergo addition reactions. So if we take bromine and if we take an alkene and treat it with bromine, we get anti-addition, right? Remember that? So aromatic rings, however, are so stable that they do not undergo such reactions. So you could suppose, you could make a mechanism for this that would make some sense. Boom, boom, right? And you, just like this one starts out, right? Boom, boom, okay? Well, this one works. This one actually goes forward, but this one does not. Why? Why does it not go forward? Well, let's think about this from an energy standpoint, something you couldn't predict just by looking at the electrons. So if you take cyclohexene, and add H2 to it, right, you get a similar reaction. Of course, we typically take some kind of metal catalyst with this, but we get 120 kilojoules out of it. All right, 120 kilojoules out of it. Well, we would expect then that if these two double bonds were completely unrelated, then we would get minus 240 out of it, right? Can you see that? If they were completely unrelated, you added H2 across both of them to get cyclohexane, you get 240. Well, they're not unrelated because of resonance, right? Resonance. So they're not unrelated, and so we actually only get 232. Because they're more stable, right? So we're losing that if we put H2 across there, we're not. It's already starting out with a lower potential energy. Now look at this. If we did this, we wouldn't expect minus 360, right? Because we know that these double bonds have something to do with each other, resonance. But we would expect to get. Oh yeah, it says 360 right here, right? Yeah, but you would expect there to be some extra benefit because of the resonance, right? Nevertheless, it's not 360, and it's not 360 minus 16, right? Can you see there's a difference of 8 here from 240? 8. So you might say, well, maybe it's 8 times 2 is 16. So maybe this is minus 3. I don't know, what's this? 44, right? But it's not. It's even lower than that, substantially lower than that. Look at that, 208 is what we get. So what that means is that 3 double bonds is actually more stable than even 2. Wow. Okay, why is that? This is a big deal. The heats of hydrogenation can be used to verify or quantify aromatic stability, or in other words, give us some sense of what it means to be aromatic, what kind of stability is conferred by aromaticity. And this is it right here. Instead of being 360, it's not 360, it's not 344. Wow, it's minus 208. That's all we get from hydrogenation. Okay. So does every fully conjugated system have aromatic stability, right? So you might say, well, maybe it's just because these guys are resonating, right? And these guys are resonating. And that would make some sense. However, some fully conjugated cyclic compounds are actually reactive rather than stable. Okay, so for example, if you take these two, what's these? Cyclobutadiene. If you take cyclobutadiene will react with another molecule of cyclobutadiene and make this mess, okay? And then these guys, these bonds will come over here and will actually make cyclooctatetraene, right? Cyclooctatetraene. Wow. You mean to tell me that these guys are so reactive that they're automatically going to make that? That's remarkable. There's a couple reasons why. There's a couple reasons why, but before we do, let's just look at the rules. So an aromatic compound fulfills two criteria. There's actually two criteria here in the first one. A fully conjugated ring, fully conjugated with overlapping p orbitals, okay? So look at this. What's the hybridization of this carbon right here? It's sp2, right? What's the hybridization of this one? It's sp2 because it's got 3 bonds, right? 3 bonds, sp2 and sp2. I'm sorry, 4 bonds, but 3 that are only 3 electron groups coming off of each one, right? It's got a hydrogen coming off here. I know, someone in the comments is going to get real mad about me saying that. But here's an electron group, here's an electron group, and here's an electron group. And so it's please excuse me, it's only sp2. All right, what about this one? There's a hydrogen coming off of here, but there's only 3 electron groups coming off this carbon right here, right? That electron group, this electron group, and that electron group, okay? So it's also sp2, 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 right? You see where I'm going with this? All the way around, sp2, 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 right? So these both are fully conjugated rings, and they have overlapping p orbitals. So, right, you know that there's an unhybridized p orbital here. So the valence orbitals of carbon, 3 of them are mixed together to hybridize an s and 2 p's, but there's an unhybridized p orbital, which is not part of the system here, which I'm going to draw, you know, pretend like it's sort of out of the plane. Right? And these guys have side-to-side overlap. Side-to-side overlap. See it? Side-to-side overlap, okay? So, so a fully conjugated ring with overlapping p orbitals, which I do have here in cyclo-octa tetraene, right? You see it? Cyclo-octa tetraene. In that molecule, I do have a fully conjugated ring with overlapping orbitals, but they also have to meet Huckel's rule. What is Huckel's rule? So Huckel's rule is an odd number of electron pairs, or 4n plus 2 total pi electrons, where n is equal to 0, 1, 2, 3, or 4, or so on, okay? So what's an odd number of electron pairs? Well, you could have 1 number of electron pairs, right? That would be electron pairs, which is equal to 2, right? 3 electron pairs, which would be how many pi electrons? 6, right? Can you see that? 5 electron pairs. How many pi electrons are in 5 electron pairs? 10, right? Can you see that? Okay, so these are Huckel numbers. These numbers also satisfy 4n plus 2, right? So if n is 0, then 4n plus 2 is 2. If n is 1, then 4n plus 2 is 6. If n is 2, 4n is 8, plus 2 is 10, right? See that? Okay. So here's 2 ways to think of that. An odd number of electron pairs, or 4n plus 2 total pi electrons, where n is a natural number. 0, 1, 2, 3. I think these are counting numbers, or natural numbers. I forget what those are called. All right, so the aromatic compounds, they've got to fulfill 2 criteria. A fully conjugated ring with overlapping p orbitals. That's kind of 2 criteria right there, isn't it? And they also have to meet Huckel's rule. That is the pi electrons. The number of pi electrons has got to meet Huckel's rule. That's another big deal right there, right? We've got to watch out for that. It's the number of pi electrons. All right. So finally, let's look at a rule that's given to us by a guy named Frost. Okay. So Frost says, you know what, we can do this with molecular orbital diagrams. And I'm not going to go back through. Klein does a good job, I think, going through molecular orbital theory, which I think is valuable. But we can do this without that. If you use Frost's rule, and here's Frost's rule. Number 1, draw a circle. Number 2, inscribe a polygon, making sure that one of the connecting points is at the bottom of the circle. So if we're trying to predict, watch this. If hepta, right? If something that's got 7, do you see hepta right there? Hepta blanca ene, right, is aromatic. We would draw a polygon with 7 sides there. Okay, you see that? Polygon with 7 sides. And make sure that you've got a vertex at the very bottom. Okay. Next, draw a horizontal line at each intersection, and this is where this is really just a molecular orbital diagram. Okay, so we draw a horizontal line here, 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 every vertex, right? Okay, and then draw a dotted line at the halfway point. 1, 2, dot, 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 dot. No, I'm not counting that. Okay, draw a dotted horizontal line through the center of the circle, and then erase the circle polygon. You could just leave the circle there, it doesn't matter. Now, identify all the bonding molecular orbitals. That's everything below the dotted line. And if there's anything on the dotted line, it's non-bonding. And if there's anything above it, it's anti-bonding. Identify all the bonding molecular orbitals. That's everything below. Okay? And all the anti-bonding molecular orbitals and everything above. Now, find all pi electrons and assign. Just a second here. Okay, let's go on the next slide here. So, if you have one bonding orbital, look at this here. Where am I? You can only have 2 electrons, right? If you've got 3 bonding orbitals or bonding molecular orbitals, you can have 6 electrons, right? See that? If you have 3 bonding molecular orbitals, I guess with what is this? Benzene, right? That would be, right? And you've got now a 7-membered ring. You can still only have 6 electrons, right? You see that? And if you've got an 8-sided, that's an octagon, octa blanca ene, you can still only have 6 pi electrons, right? Because there's only 3 bonding molecular orbitals. If you have a nona ene, you now can have 10. See that? Because these are all bonding because they're all below that dotted line. And then a 10-membered ring, you could have 10 electrons. See it? Okay. All right, note that the number of bonding orbitals is always an odd number, which is just exactly what we got Huckel's rule. So Frost's circle, I mean, it's great. This is going on YouTube, so I hate to criticize it too loudly. But frankly, we can get all this same information by looking at the criteria which I gave you before. So note that the number of bonding orbitals is always an odd number. Aromatic compounds will always have an odd number of electron pairs. Okay? And I think that is it. Now, you need to go practice with conceptual checkpoint 18.9. Good luck.